Good morning, dear student. In last lecture, we will discuss regarding to the metallocene. So, what is metallocenes? What are the different reaction which is shows by metallocene, and which metal ion generally forms this metallocene? So, in today's lecture, we will discuss regarding to the nature of this metallocene, that is either it is diamagnetic, paramagnetic, what it is homo, what it is lumo, and then what its magnetic moment, that is how many unpaired electrons are present in this metallocene. So we will discuss one by one. So we already discussed, that is from vanadium, that is vanadium, chromium, manganese, Fe, cobalt, nickel. These metal ion generally forms the metallocenes. So we will discuss one by one. That is the first metallocenes, that is Vp, that is vanadium Cp2, vanadium Cp2. So in this complex, vanadium is in +2 oxidation state. So its configuration is 4s0 3d3. So it contain only 3 electrons. So if you consider the d orbital splitting for this complex, then it is like this. That is, this is your bonding, this is your non bonding orbital, and this is your anti-bonding. So you should remember this d orbital splitting in case of metallocene. So in this case only 3 electron is there. So first, second, and third. So it has 3 unpaired electrons. So 3 unpaired electron, and therefore it is paramagnetic in nature. It is paramagnetic in nature. If you consider its dipole magnetic moment, that is mu, which is equal to, so it contains 3 ampere electron, therefore the Bohr magneton or magnetic moment is up to 3.90 bm Bohr magnet. Again, if you consider the last electron is present in this non bonding orbital, so this is your E2g, this is your A1g, and this is your E1g antibonding, E1g star. So the last electron is present in non-bonding A1g orbital, and this A1g is your HOMO in this case. So A1g is HOMO, highest occupied molecular orbital. So the last electron present in the orbital is considered as a HOMO, that is highest occupied molecular orbital. So in this case, the HOMO is A1g, and the LUMO is antibonding E1g star orbital. E1g star orbital, that is your LUMO. So you should remember all these things. That is, you should first draw the d orbital splitting, then place the electron. So all these metallocenes are a low spin complexes, except magnocenes, in which it is a high spin complex. So you should remember its nature, that is either it is paramagnetic or diamagnetic, then its magnetic moment, then what is its HOMO, and what is its LUMO. So this is regarding to the VCP2, vanadocene. So let us consider the next, that is chromocene, that is CrCp twice. Again, if you consider the chromium is in +2 oxidation state, so it is 4s0 3d4 configuration. So one electron is one electron is more as compared to vanadium. So in this case, again, if you feel the electrons, then again it is E2g, then A1g, and then it is E1g star. So there is a total 4 electrons. So first, second, third, and the fourth electron is not go into this antibonding orbital because the energy gap between these two A1G and E1G star orbital, that is non-bonding and antibonding orbital, is very high. The energy gap is very high, and therefore uh, lots of energy is required to transfer the electron into this E1G antibonding orbital, and therefore instead of going into this antibonding orbital, the electron goes into this E2G orbital, lower energy E2G orbital, and there is a pairing of electrons. So in this case, if you consider, there is a 2 unpair electron in case of these chromosomes. Again, if you consider, it has 2 unpair electrons, therefore it is paramagnetic. Again, if you consider its magnetic moment, so 2 unpair electrons, so magnetic moment which is equal to 2.90 Bohr magneton. And again, you consider what is its HOMO, that is highest occupied molecular orbital, then again it is A1G. A1G is your HOMO, and what is your LUMO, that is the E1G star, that is antibonding orbit, it is your LUMO. So you should remember all these things regarding to this chromosine. So let us discuss the next metallocene, that is magnocene. Thus magnocene, that is MnCp twice. So in this case, Mn is in +2 oxidation state, so 4s0 3d5 configuration. But this magnocene is not a low spin complex, it is a high spin complex. That is, the electron is not pair in this case, the electron goes into antibonding orbit. So again, if you draw the d orbital splitting, then in this case the energy gap between this non-bonding and antibonding is very small. The energy gap between this non-bonding and antibonding orbital is very small, and therefore in this case the electron is not pair, the electron goes into this antibonding orbital. So there is a total 5 electrons, so first, second, third, fourth and fifth. So in this case there is no pairing of electron. Instead of pairing, the electron goes into the uh, antibonding orbital, that is E1G star antibonding orbital. So in this case again it is a paramagnetic. So all, if you consider, there is a 5 unpair electrons, 5 unpair electron. Again, the magnetic moment mu, which is equal to 5.90. So if you consider its HOMO, highest occupied molecular orbital, then it is E1G star, that is antibonding E1G star. It is HOMO for this MnCp2. And if you consider the LUMO, that is lowest unoccupied molecular orbital, then in this case the LUMO is E2U antibonding. So this is your E2U antibonding. So you should remember all these things regarding to this magnocene. So it is a high spin complex, it is not a low spin complex. So in this case total 5 unpair electron, and its HOMO is antibonding E1G star, and its LUMO is E2U antibonding. So this is regarding to the MnCp2. But if you consider the substituted MnCp2, so this star indicate this cyclopentadiene is substituted. So if you consider the substituted metallocene, that is magnocene, then it is a low spin complex, a low spin complex. If you consider a structure, that is Mn, it is attached to this cyclopentadiene ligand, and all these sites are substituted again. Yeah. So all these both the cyclopentadienyl ligands are substituted. So in this case, the electron is not goes into the antibonding orbital. So instead of going into this antibonding orbital, it will pair, and again we consider the splitting of d orbital, and in this case there is a 5 electrons, first, second, third, fourth, and fifth. So the electron is not goes into this E1G antibonding orbital. The electron is pair into this E2G bonding orbital. So in this case, the number of unpaired electron is equal to 1. So number of unpaired electron is equal to 1. Again, if you consider the magnetic moment mu, which is equal to 1.90, then it is paramagnetic. So one unpaired electron, therefore it is paramagnetic. So if you consider its HOMO, highest occupied molecular orbital, then it is A1G. HOMO is A1G, and the LUMO is your E1G star. So you should remember, all other metallocenes are low spin complexes, but this magnocene MnCp2, it is a high spin complexes. So in this case, the electron goes into this antibonding orbital, while the substituted metallocene is a low spin complexes. So let us consider the next metallocene, that is ferrocene. So let us consider the ferrocene. So we all already discussed the ferrocene, that is FeCp twice. So again Fe is in +2 oxidation state. So 4s0 3d 6. So total 6 electron is there. Again E2G, A1G, and E1G antibond. Then first, second, third, fourth, fifth, and sixth. So in this case, all electrons are pair, and there is no unpaired electron, and therefore it is diamagnetic in nature. So the ferrocene is diamagnetic in nature. Again, if you consider the mu, that is magnetic moment, so no unpaired electron, therefore magnetic moment is 0. Again in this case, the HOMO, highest occupied molecular orbital, is A1G, and the LUMO is E1G antibody. So you should remember, the ferrocene is diamagnetic in nature. So all electrons are pair. So it is an 18 electron complex. The ferrocene is 18 electron complex. Not all metallocenes are 18 electron complex. Ferrocene, cobaltocene, and nickelocene generally are 18, 19, and 20 electron species, but less than 18 electron complex is also possible. So not all metallocenes follows the 18 electron rule. So let us consider the next, that is cobaltocene, COCp twice. So again cobalt is in +2 oxidation state, so 4s0 3d 7. Again we consider the filling of electrons, then it is first, second, third, fourth, fifth, sixth, and the last electron goes into this E1G antibody. So in this case, one unpaired electron, so it is paramagnetic in nature. Paramagnetic in nature. Again mu, which is equal to 1.90, because presence of one unpaired electron. Then if you consider its HOMO, then it is E1G star, E1G star antibonding E1G star, and its LUMO is again E2U antibonding. So this is regarding to the COCp2. Similarly, if you consider, if you consider The next, that is nickelocene, NiCp twice. Then again nickel is in +2 oxidation state, so 4s 0 3d8 configuration. So again we consider here first, second, third, fourth, fifth, sixth, seventh, and eighth. So again it has two unpaired electron, two unpaired electron. So it is paramagnetic in nature, paramagnetic in nature. Again, if you consider its HOMO, then it is E1G antibonding, and its LUMO is your E2EU antibonding, NiCp2. So this is regarding to the NiCp2. So this is regarding to the its paramagnetic, diamagnetic nature, magnetic moment, what is its HOMO, what is its LUMO. So many times the question is asked on MC bond length. So in previous lecture we will discuss, that is, as the number of unpaired electron is increases, as number of unpaired electron increases, then the MC bond length is also increases, then the MC bond length is also increases. So if you consider all these metallocene, so in which metallocene, if you consider the unpaired electron, then MnCp2, MnCp2, it contain 5 unpaired electron, 5 unpaired electron as compared to all other metallocenes. So in this case, as the number of unpaired electron is increases, the MC bond length is increases. So the metal atom and carbon of cyclopentadiene, MC bond length is highest for this MnCp2 than all other metallocenes. So it contains maximum unpaired electron, therefore it has high MC bond length, high metal carbon bond length in case of this magnocene. So this is regarding to the paramagnetic, diamagnetic, HOMO, LUMO, and the magnetic moment of the metallocenes. So in last lecture we also discussed some important reactions of the metallocenes, that is Prell-Krupp, alkylation, and acylation reaction. So it also shows, this metallocene is also shows different types of reaction, such as Munich base reaction, Munich base reaction. The reaction is very simple, that is reaction of ferrocene, that is FeCp twice plus aldehyde in presence of dimethylamine, NH dimethylamine. So in this case, this dimethylamine and aldehyde forms a Munich base, that is, it will forms a Munich base, that is CH2 positive N Me N Me, and it is act as a electrophile, it will act as a electrophile, and this ferrocene, this electrophile is attack on this ferrocenes. So this is an important reaction in organic chemistry, Munich base reaction. So in this reaction, if you consider how this electrophile is formed, that is, in this case this is your aldehyde and this is your N Me Me and H. and the lone pair of this nitrogen, it will attack on this carbonyl, that should be O minus. So what you get here, again HCO minus, then here the hydrogen, again here nitrogen attached to H, then it is Me, and then it is Me. So in this case this O minus will abstract this proton, and what you get here, HCOH. So this nitrogen having a positive charge in this case. So HCOH, H, again N, Yummy, and Yummy. So again in presence of acid, it will takes a proton, this lone pair of oxygen abstract one of the proton, and here what you get, next step. So if you consider, so again HCOH having nitrogen and Me, and Me, and this hydrogen is there. Again in presence of acid, the lone pair of oxygen, it will abstract these as protons, and what you get here, HCOH2 positive, N, Yummy, and here H, and again with removal of this water molecule, so minus H2O. So what you get here, CS2N, Yummy, having positive charge. So this is your reactive electrophile, and this, it will shows reaction with ferrocene, that is this is act as an electrophile, and this ferrocene, that is Fe, again a reaction with CS2 positive, N, Yummy. So it is act as a nucleophile. So what is the product? So in this case, see here CS2, N, Yummy, and Yummy. So no doubt it will shows product of alkylation, acylation. It also shows the Manich base reaction. It is very important in organic chemistry, that is Manich base reaction. Again, if you consider the different reactions of this ferrocene, it also shows the Willsmeyer Hack reaction. So we student, we are very much familiar with Willsmeyer Hack reaction. Willsmeyer Hack reaction. So this ferrocene, it does also shows Willsmeyer Hack reaction, that is ferrocene in presence of dimethylformamide and POCl3. Dimethylformamide, POCl3, it will gives the aldehydic ferrocene, CHO. So we are very much familiar with this Willsmeyer Hack reaction. So you should cover the mechanism of this Willsmeyer Hack reaction. So in this reactions, that is in presence of dimethylformamide and POCl3, the ferrocene having the aldehydic group is formed. So it will shows Manich base reaction, Willsmeyer Hack reaction. Again we consider the direct reactions, that is direct nitration and halogenation reaction of this ferrocene is not possible. So you should keep in mind, that is CP, again CP. So direct nitration HNO3 or halogenation I2 or Cl2 is not possible, because in this case this is an 18 electron species. In presence of a strong acid or strong oxidizing agent, the ferrocene get oxidized So this ferrocene get oxidized. So oxidized means it will lost one electron and convert into 17 electron species. So instead of forming a product, it will form a cationic species having a positive charge. So direct nitration or halogenation, that is oxidizing agent I2Cl2, does not give any reaction. Instead of giving the product, it will lost one electron, so it undergo oxidation reaction and forms a cationic species. So this is regarding to the nitration of this ferrocene. Again, one more important reaction of this metallocene, it will shows lithation, that is lithation reaction. Lithation. So what is this lithation? Lithation. So if you consider this lithation reaction, introduction of metal to this cyclopentadiene ring is known as lithation reactions. So introduction of metal atom to this cyclopentadiene ring is considered as a lithation reaction. So generally Fe, that is ferrocene, in presence of tertiary butyl lithium, it will undergo monolithylation reaction, that is your Fe, and then monolithylation monolithylation. And in presence of n butyl lithium, it undergo dilithylation reactions, that is another lithium to the cyclopentadiene. So this complex, this lithylation complex is very much important in organic chemistry. It will shows lot of reactions. So this lithylation is the important reactions of these ferrocenes. So this is regarding to the all about metallocenes. In next lecture we will discuss some remaining points regarding to the metallocenes. What are the question asked in CSIR NET exam and SET exam, and the remaining points of this chapter. Thank you.